In this video, I'm going to be going through the different allotropes of steel, the different cubics of steel. So we're going to go austenite first. And so this is where I normally play the Austin Powers music. But what we want to remember is that it's often referred to as gamma steel. So alpha, beta, gamma. Gamma is the third Greek letter. And austenite, it does not exist at room temperature. It only exists over this line of 723 degrees. We call this the lower critical temperature. This is the lower temperature where we start to get austenite. At this line here, the upper critical temperature, that's where we have 100% austenite. So in between, we have some amount of austenite and ferrite, we're going to learn about later, and some amount of austenite and cementite. Now, the upper critical temperature changes depending on the carbon content. The lowest point is this point here called the eutectoid point. Now, we're going to talk about this in a bit more detail later, but that point here we can call the V, right? The V in this diagram. Now, that's V is the eutectoid point. It comes from a Greek word for happy melting because usually the eutectoid point is where things melt the most. But I want to remind you that all of this is solid. All of this is solid. Austenite is just a very hot metal, right? Red hot. Now, if it's less than, we use the Greek word hypoeutectoid. Hypoeutectoid means less than eutectoid. It means it has less carbon than the eutectoid, right? And in that case, we get these two colors. We get the pink and the blue. If we're over, we get hypereutectoid. Hyper means more, right? And so that's so here we have O if it's to the left of the V point, and we have ER if it's to the right of the V point. Now, some of you may have noticed that that spells a word in English, the word over. It doesn't have anything to do with this, it's just a mnemonic. Now, hypereutectoid are orange and green. Now, if it's right on the eutectoid, we get something called perlite, which we're going to talk about in a bit. The point I want to say is that this line is different for different carbon content. So this line here is called the upper critical temperature, and it can be 900 degrees for pure iron, and then its lowest point is where the eutectoid point, where it's 100% perlite, and then as the carbon content increases, the upper critical temperature also increases. So we'll talk more about crystal what these grains look like when we zoom in on them in a bit, but for the moment we're going to go back to this picture. And in this picture, so we've now talked about austenite, red hot, 10 out of 10, right? It's got 10 in the name. Okay, so austenite is also known as gamma steel. It is a face-centered cubic. Look at that face. To help you remember, look at that face. Now, we also have ferrite. Ferrite is a body-centered cubic. Now, you can see that ferrite only exists as a hypoeutectoid. O with a O, you know, like O for orange, O for Oscar. Hypoeutectoid. It only exists below 0.83% carbon. Now, as we, okay, so it is a alpha, is also referred to as ferrite. Alpha steel or ferrite is a body-centered cubic. And that's, to help you remember that, we have a picture of this ripped ferret, right? It's very, very good body. Now, on the other side, on the hypereutectoid, hyper, ER, right? Like there used to be a TV show with George Clooney. I don't know if you guys know who did anyone know who George Clooney is? There we go. He got his break in being a doctor in ER. And then he was Batman. He was Dr. Batman. And then like he went on to be very successful in the Ocean's 11 movies. Okay. I thought they were pretty good movies. My children did not enjoy them. Okay. Well, they didn't like the ones with George Clooney. I think that they enjoyed the one with the Ocean's 8. Okay, so what we're going to look at is in this area, in the hypoeutectoid, we have another one called cementite. Or I've worked with teachers who I believe mispronounce it as cementite. So here I have a picture of some semen, right? Okay, now what we're going to look at is, so perlite is a mixture, it's a stripy mixture of ferrite and cementite. Ferrite and cementite. So you can imagine these black areas as being ferrite and these white areas as being cementite. And it forms grains of these stripy layered crystals, which we call, or lamella is the term we use to describe layered layers of So perlite is layers of ferrite and cementite, and I'll show you what that looks like. Now this diagram is not a bad way of visualizing what the crystals look like in different areas. So if we zoom in on any section, it kind of gives us a pretty good idea of what is going on at that temperature and at that carbon content. So steel melts at 1536 degrees Celsius, no matter what the carbon content. But it can be a lot lower over at this eutectoid point, which is at about 4.3% carbon. At 4.3% carbon, it will melt at a much lower temperature at about 1147 degrees Celsius. Now, we're not really interested in that part of the graph. We're only zooming in on this section here, right? We're only zooming in this section here. But just to quickly run through, just to remind you that it goes from liquid to liquid plus austenite, and eventually below this line, we're going to have full austenite. In this area here, we have full austenite. So we're just going to look in this zoomed area. And in this zoomed area, well, actually, we don't want quite that much. We want about here. That'll do us. In this zoomed area, we have our eutectoid point, which is what percentage of carbon? It's less than 1%. It's what percentage of 1%? 83, yeah, that's right, 0.83% carbon, because I am born in 83, so you can remember as the Punset number. Okay, so at this line, if you look down this line, can you see how the whole thing here is just perlite? And see how the perlite is these grains, right, these big areas, and they're stripy of black and white stripes. What are the black and white stripes? Black and white stripes are perlite, and perlite is made up of layers of It's layers of, what do we call the low carbon steel? It's got a good body. Ferrite. And it's got layers, the other layer, the second layer that it's sandwich layers of is, think of the navy, cementite. So ferrite and cementite. Perlite is layers of ferrite and cementite. Now, as we start to go on this left-hand side of the line, in the this area here, this square here, all of this stuff here, to the left of the line is hypoeutectoid. It means under the eutectoid. It means its carbon content is under the eutectoid. Now, just to quickly to refresh, if we cool 0.83% carbon, we have a good video on this that we'll watch in a second. If we cool 0.83% carbon, it's going to transform from austenite into perfect amount, into entirely perlite. You know what? We're actually going to watch that video. We're going to click into that video. We just need to find the right set of notes. Bear with me. I'm going to have to do maybe a short edit. Okay. So in this video, what we're watching is some steel be put into a furnace, heated up until it's red hot. Let's see what happens. As the temperature heats up, what do we have here? This has got 0.83% carbon. So what are we seeing? We're seeing all of our grain structures are, starts with P, perlite. Excellent. All of these grains are perlite. They're layers of ferrite and cementite. As we get to 723 degrees, well, we start to see what's forming. We start to see crystals of what forms at higher temperatures. So hot, red hot. Austenite. By 750 degrees, it's fully formed into austenite. Now, they're going to cool this, and they're just going to let it cool in the air. What would that process be called when we let it cool in the air? Normalizing, exactly right. Now, as it cools in the air, what we can see is we can start to see these little grains form. These small. We're going to look at what grains look like as they form from liquids or something like that. But this obviously is not a. This is an animation. This isn't a. They're not photos. But what we can see is small grains starting to form within the austenite. What are those grains? Starts with P. Perlite. It used to be called something else. It used to be named after some person, the discoverer. But then they said, you know what? That looks a bit like mother of pearl. Do you know what mother of pearl looks like? someone said, it looks a bit like mother of pearl, right? I don't even think it looks that much like mother of pearl. But they said, someone said it looked like mother of pearl, and then they took the name away from the person and then called it Perlite. I don't even know that person's name, but I feel sorry for that guy. Well, that person. Okay, so as it cools, we can start to see that we're getting perlite crystals forming. Yeah, and eventually they form to the point where those crystals bump into other crystals. Now, what's interesting is because we normalized, are these crystals bigger or smaller than the predecessors? They are smaller because when we anneal, we get big grains. When we normalize, we get small grains. Now, I use the term equiaxed grains. Equiaxed means roughly equal in all dimensions. It means soccer ball shaped, not sausage shaped. Because when we work harden, we get long, elongated grains, which which are harder to form and give us additional strength. But when we normalize, we're going to get small, equiaxed grains. When we anneal, we get large equiaxed grains. Equiaxed means roughly equal in every direction. Yeah, it's obviously not spherical, but it's roughly equal in every direction. They're not elongated in any one particular direction. Now, while I've got this video open, they do show some tempering in this video as well, right? So they show that when we cool quickly, what we form is these needle-like grains. What's an adjective to describe needle-like, to say needle-like? Acicular. Acicular means needle-like. We'll come back to tempering later. What we want to look at in the meantime, is we want to look at when grains form. So here they've got some molten aluminium. Well, okay. First of all, here's what I should start with, and I've kind of gone a bit backwards here, but this will do. We can see some grains with your eye, right? So right now in our room, we have a projector that sits on a steel tray. Yeah, you can see that. On the bottom of that, you can see those grains because zinc grains can be huge. They can be 5 millimeters. They could be potentially 50 millimeters across, right? Steel generally has very small. So here we can see these grains with our eye, with the naked eye, very, very easily. But for smaller objects, for some other materials, we can't see their grains. They could be microscopic, right? We need to look at them in the microscope. So what we have here is we have a very smooth surface. We can't see any grains. Right, we polish it, but then we etch it with acid, and when we etch it with acid, we can now see the grains. See how the grains are now visible? Yep. Okay. Now, for some materials, the grains are microscopic. For other materials, the grains are very large. I'm later going to show you some zinc ingots where the grains are very clear. Right, copper. Now, what we're going to show you is the formation of grains in the case of aluminium grains forming, so it can be more easily filmed. Okay, so when we zoom in, what are we looking at? Okay, so to start off with, we have very small points. With the first, I like to think of like if people are running around the room, and they then hold hands and sit down. So when they're liquid, they're running around the room. But occasionally, there's going to be that one kid who sits down first, and when they sit down, they say to their friend, "Hey, sit down with me." And from that point, it's going to continue to grow until eventually every kid is sitting down. As everyone gets, they're not less excited, right? As we reduce the heat from a molten metal, the atoms become less excited. And eventually, as they calm down, they're going to collect and they're going to hold hands. And when they hold hands, we're going to call that a grain or a crystal. So there's always the first point, the first kid, the first atom who sits down and who tries to hold hands with other kids to get them to sit down. We call that the nucleation point. That's the center point. That's where things start. So we have nucleation points, and we can see that from these nucleation points that things start to grow. So let's go back. So somewhere around here, there's a nucleation point. There we go. There's a nucleation point. And then the next step is they then start to form little trees. The Latin word for, I'm going to say Latin word for little tree is dendrite. So dendrite is a little tree. So you can see these little trees, they're starting to branch out. Now eventually you'll start to get secondary branches, right? That's the third step. So we have nucleation, dendrite, secondary branches. We can see branches growing from branches. And then eventually they start to bump into each other. And when they start to bump into each other, we get grain boundaries. As they start to grow into each other, we start to get grain boundaries. So when we look at steel, we're looking at those grain boundaries. Now, what are they showing here? Okay, so I think they're showing if you cold work, you can get elongated grains. Right, so if we roll steel, if we cold roll steel, do you see how those grains are elongated? Elongated grains are stronger, but generally we don't want elongated grains. We want small equiax grains, because that way our strength is going to be uniform in every direction. And that's generally a better thing for engineering, is to have strength that's uniform in every direction. So when we work hard and we get elongated grains, how do we get rid of those elongated grains? Starts with an N? Normalizing, exactly right. Okay. So you can see how they've simplified this diagram. They've shown that they've got these elongated grains, and we're going to normalize to remove those grains. We can here they're actually annealing. That's why we get the big grains, and they're doing some testing. This is a hardness test to show how hard the material is, and then later we can do a toughness test. So they're stretching the material using a tensile test. And eventually they'll do a toughness test. Okay. Okay. So here we're looking at a material. This material, is it entirely stripy perlite? No, it's not entirely stripy perlite. You can see areas where there's no stripes. So that means this is a hypoeutectoid. Right? From this appearance, it's hypoeutectoid. So what does that make these other crystals here? Let's have a look. That's a bit confusing for you guys. So let's have a look. Okay. If it's a hypoeutectoid, we have perlite, and what's the other thing? Perlite and ferrite. Okay. So that's what we're looking at here is ferrite. So the ferrite appears as the lighter green, and the perlite is actually stripes. And as they zoom in, to make that clearer, they're zooming in to try and give you the idea of what's going on here. So as they zoom in, we can see here, we have ferrite and, what do we call this one? Starts with a P? Perlite, excellent. Okay, ferrite and perlite. But to simplify it, the ones they used were just pure. Okay, so what they're showing here is they're saying ferrite is pure. They're saying is iron, right, with some small amounts, tiny amounts of carbon in it, whereas the perlite is a combination of iron and iron carbide. What do we call iron carbide? Navy? Cementite. That combination is what we call perlite. Now, if we go to something that's pure perlite, as the carbon content increases, do you see how we get more and more perlite crystals? Yeah, as the carbon content increases, we get more and more perlite crystals. This is a picture of perlite. Does it look like mother of pearl? I guess it does. I guess it does. Now, here they're showing a diagram which is pure perlite, and we're back to our normalizing. Okay, so we saw that if we anneal, annealing is a way of removing all the stress, removing all of the elongation, and giving us large, low-stressed grains. If we normalize, we're going to get small equiax grains. Okay, now let's go back to our picture. So at this point, we now should have a fairly good understanding of perlite. We have a good understanding of ferrite. Ferrite, we can think of ferrite as being almost entirely iron, with a very small amount of carbon, right? The tiniest amount of carbon squashed in between that lattice of just regular. Imagine if you had a 3D grid, or imagine, perhaps the better example is, imagine you went to the shops and you saw all of the apples stacked. Yeah, you can imagine that. Now, imagine I said to you that those apples are iron atoms. And then I took a grape they just squashed some grapes in between, and I said that was carbon. There's only so many grapes you can squash in between before it really is going to start disrupting those apples. Yeah, that's ferrite. Now, iron carbide, it has its own crystal structure. Well, it's actually Fe3C, so it means that there's three ions for every carbon. Let me see if I can find the picture of that. It looks like this. So austenite is a face center cubic, ferrite is a body center cubic, cementite has this zany crystal structure that we don't need to know about. Real good? Okay. But we know that it's 3 carbons, 3 ferrites for every carbon. Okay. So, we've talked about different crystal structures. We've talked about hyper and hypoeutectoid. Now, later, we're going to learn that generally low carbon steels, right, are very soft. You use them for things like chains. Yeah. Whereas what we typically use is mild steel. Mild steel has 3% carbon, 0.3% carbon, also known as 1/3%. 1/3% of carbon. Now, where do we use mild steel? Everywhere. It is the ubiquitous material that we use. It's the most important engineering product. It is used everywhere. Now, 0.6, we might call that medium carbon steel. Where do we use 0.6? Railways, right? The railway rails, they're made of 0.6% carbon steel. 0.8, or eutectoid steel or high carbon steel. Well, that's starting to get to things like files, and then high carbon steel is things like punches. I'm led to believe that ICBMs, intercontinental ballistic missiles, they also used high carbon steels. Where are they strongest? The strongest is perlite. You have the most strength when you're at full perlite. The only reason you want to go past full perlite is because you want hardness. Yeah, you start getting additional hardness past that point. Okay. I think that's a pretty good introduction. So now we're going to have a look at this picture again. We're going to open that up again. Okay, so we're going to talk about down in this zone. In this zone here, we have, if we have 100% ferrite, well, it's just going to be white crystals. Yeah, a whole bunch of crystals that all look the same. Yeah, it'd be this part, this corner here. If we start to get to mild steel, well, if we have a look at that, we have kind of in this gap here, we kind of have, it's maybe 50-50, a little bit less than 50-50 perlite. Yeah, so mostly ferrite, a little bit, and then we have some perlite crystals. And then as we get to like 0.6% carbon, well, that's around this area, we're going to have more perlite. Once we get to the eutectoid point, we're going to have, as we can see here, 100% perlite, just like on the video. They don't show us on the video what happens if we get to hypoeutectoid. With hypoeutectoid, we tend not to get solid grains of cementite. What we tend to have is we tend to get cementite forming around the outside. And you can see that as the carbon content goes up, we have more and more cementite or iron carbide building up around the outside boundaries around each of these grains of perlite. We good? Okay. Remember, here we're going to have very hard, here we're going to have very soft, and where we have our most strength, where it's just right, is at the Punzet number, the Goldilocks Punzet number, which is where we have our maximum strength with still good ductility. Okay, at 100% perlite. So now we're going to quickly revise the heat treatments with a mind to the fact that no. Oh no, I've lost it. We're back, hopefully. Okay, we're back for real this time. Okay, so yeah, we've talked about everything on this picture, so let's go to our next one. So the next thing we're going to talk about is annealing. Now, I want to really drive home that if these memes don't work for you, that's fine. They're just mnemonics. They're just a tool to help you remember. If you just remember, you want to make some flashcards and just learn these details, that's fine. That's why I've set homework where I've asked you to summarize them. But what are the key takeaways that we want to remember? To anneal, we heat to 100% austenite, or red hot. Cool slowly in a furnace. Annealed steel has large, unstressed equiax grains and is soft and ductile. We use it for things like canned food. Yeah. Now, in the last video, I went through all the memes. I talked about Big Neil, and we said aloha Neil. But this time around, I'm just really going to focus on the facts, right? Annealing is when we heat, in each of these 3 heat treatments, we're going to heat up to 100% austenite, and then we're going to cool. In this case, we cool, this is the slowest. We cool slowly. We cool it by keeping it in the furnace and slowly reducing the temperature in the furnace. What it results in is big equiax rounds. That's why we've got Big Neil there. Right? There's low stress, which means that you can drop the can of food on the ground without it splitting open. It's just going to dent. It's not going to split. And that's a good thing. Well, that means it's good for its application. Okay, the next one is when we're going to cool in air. Can anyone remember when we cool faster? We cool faster in air. We just take it out of the furnace. We just leave it in the air. What are we going to get? Starts with an N? Normalizing. Okay, so normalizing, right? I wish I could remember the song. It's harder. It's better, right? We generally use it. It doesn't have the elongation. I would say it's more commonly used, therefore better, right? Harder, better. It's stronger, right? It has a higher tensile strength, and it's faster. It's a faster process. I want to remind you, it's faster, not fastest. Faster, not fastest. It's harder. It's stronger, but it's not hardest. It's not strongest. Yeah, it's in between. Normalizing it's the one in the middle. Okay, normalizing, first we heat to 100% austenite. Another way of writing this, heat to 100% gamma steel. Or, now I wouldn't write this in the HSC, but you could definitely write this in a trial. Heat to 100%, heat to red hot. Cool in air. Normalized steel has small, uniform grains. Harder, stronger, and less ductile than annealed steel. Okay. Lastly, we have martensite. Now, I'm not going to go through the memes here. Out of interest, who preferred the Bond memes? If you prefer the Bond memes, we'll go that's thumbs down. If you prefer annealing, prefer the Avatar memes, that's thumbs up. Bond or Avatar? There you go. Okay, the other class was Bond memes, which I'm glad I keep, because the thing is, I got rid of the Bond memes as my primary ones, because I just found that there were people who didn't know who Roger Moore was. So, Avatar, if you don't know who Avatar is, you should watch Avatar, because Avatar is amazing. Okay, so martensite. Well, first of all, we heat to austenite. Red hot. 100% gamma steel. Then we're going to quench it. Now, I've said here quench in oil. You can quench in salt water. You can just quench in water. And I tried, the whole idea here is that Korra, she's from the water tribe, right? In the Avatar cycle, it's fire, air, water. That's why I've chosen the Avatar thing. Anyway, the point is, when you quench in oil, what happens is that we go from, well, what crystal structure does austenite have? Okay, face center cubic. Look at his face, right? Yeah, baby. Now, when you cool it, it's supposed to transform from face centered cubic to body centered cubic. Right? That ferrite wants to transform into body center cubic. The problem is there's just not enough time. Because this is the fastest, it's the shortest, there's not enough time for that transformation to take place. So what happens is it goes from being face-centered cubic, and it doesn't have time to be body-centered cubic, so instead it becomes this other thing called body-centered tetragonal, or BCT. Now, I would not lose sleep memorizing that unless you're a smart kid who really wants to do well. But most people, you know what, it's very low chance that they're going to mention that in the exam, right? But by all means, remember it. What you do need to know is the crystal structure that it's produced is called martensite. Martensite is needle-like. The word we use is acicular. Acicular. You can write needle-like, that's absolutely okay. But if you see acicular, you should know that it means martensite. Martensite looks like needles. Yeah, a whole bunch of needles. If you look down here, it looks like needles. Right? I'll show you in the video. Right? So when we temper, so first they're going to quench it. Okay, they're doing an ISO test, so they're quenching, see, red hot, and then they're quenching it. And when they bring it out, we're going to do a small sample. So let's have a look what happens. So what are we starting with? What are we starting with? Perlite, excellent. Large grains of perlite at 300 degrees Celsius. They're going to heat it up until they're heating it up until it's above the upper critical temperature. Well, in the case of perlite, it is only the upper and lower critical temperature are the same. So straight away it starts forming. What are those grains that are forming? Red hot grains. Austenite, yeah, face in a cubic. And then we're going to cool it. We're going to take it out of the furnace. We're not going to cool it in air. We're not going to cool it in the furnace. Ready? We're going to quench it. It even sounds like quenched. Anyway, look at what's happening. You're getting these needle-like grains. Needle-like grains. And ready? We're going to see that a quenched avatar, not a good avatar. Ready? 3, 2, 1, bam! Just snapped. You missed it. It just snapped. Okay, so now what we're going to do is we're going to repeat that same process. We're going to heat it up, but this time we're going to remove some of that stress in that body-centered tetragonal, the BCT crystal. Right? We're going to remove some of that stress. And what happens now is by heating it up to about 200 to 600 degrees for some amount of time, it's very hard, it's very strong, but it can still be bent. Yeah, it's not going to break. Okay, so that's tempering. So the result, it's very hard, very strong, not too brittle. Where do we use this? Where is the benefit of tempering? So we said that normalizing is used everywhere. Annealing is used for canned food. Where do we use tempering?
Structures.
Not as much. I'm going to say no to structures. So the thing that comes to mind for me is swords, right? In Zelda 3, a game I played, Zelda Link to the Past is what it's called. You can get a tempered sword, right? And the tempered sword is when you take the Master Sword and it goes orange. Yeah, sorry. So for me, I always think of swords are tempered, right? Because you want swords to be very strong and very sharp. And when we think sharp, we think hard, right? Hardness is the ability to hold a sharpened edge. Yeah, so you're going to get a sharper sword if you can temper it. Now, the reason you temper it is because you don't want your sword to shatter. And that was a real problem when they were developing swords, is that you would hit your sword into the enemy's sword, or to their shield, even worse, and the sword would then shatter, and that's pretty embarrassing because you now have this broken sword. Way better to have a sword that bends, right? Have a lower carbon steel and have it not be as hard and have it bend, than it is to have a sword that shatters. Because you can bend a sword back into shape. You can't repair a sword that's shattered into bits. I'll quickly add in, very, very briefly, and I know I've talked about this in other videos. So, katanas. Okay, so katana is a curved samurai sword. And in another video, I know I have this, but when we look at the blade will have... so what they did is, the Japanese, they didn't know about tempering, right? The Japanese samurais, they didn't know about tempering. So what they would do instead is they coated half the sword in clay so that the back of it would be soft and only the front of it would be quenched. So the cutting blade would be quenched, whereas the back of the blade didn't get quenched because it was coated in clay. And then what would happen is that when they quenched it, is that you can actually see a video of... I know I've already done this before. This probably will do. It makes a great sound. I'll make sure that the audio is up. Apologies. So he's got his sword, and you see the sword, it actually bends back the wrong way and then comes back. So they start off with it straight. It didn't make the pop sound, so maybe this is not the video I'm looking for, but I have another video where it makes this boop as they put it in. The idea is that the blade actually starts straight, and then when it goes into the water, initially it bends the wrong way. It bends pointing forward towards the enemy, and then it actually, as it cools, it then returns back to the opposite direction. And you can see these marks from where the clay has fallen off. Oh, here we go, maybe this one. So you can see the person is holding the blade still, but you can see how it's bending backwards. This is in no way relevant to the engineering studies course. I'm just using this as an example to talk about why we temper swords, right? And how the Japanese, they didn't temper swords, they just quenched them. And so a student actually asked me yesterday, can you quench without tempering? I said no. And that's not entirely true. So Japanese...
Are you kidding me right now, dude? She picked my...
Great. Will I edit that out? Probably not. Anyway, so that's where you get these marks. The marks are from where the clay was protecting the process. Okay, so we've talked about the crystal structures. We've talked. Oh, where do we use it? We use quenching where we need a hard surface. So anything that has a cutting blade. Another area where we want hardness is we don't want things to wear away. So this is where I do my spirit fingers, my weird spirit fingers. What shape am I doing here? I'm doing gears, right? The teeth of gears. You don't want the teeth of gears to wear away. So the teeth of gears, they need to be hard so that they don't wear away. And then the other aspect, and this I don't like to use, but I'm going to say, if things just need to be strong, you can quench temper them just where you need strength. Right, because it does add additional strength. You can quench temper just where you need additional strength. But generally in, say, structural beams, they're not tempered, right? Structural beams, they're normalized. Everything, by default, you should think that everything is going to be normalized, unless you can say it needs to be very strong, or it needs to be wear resistant, or it needs to be sharp. Okay, that will do as our revision for heat treatment.